Okay, so welcome everyone. It's our pleasure today to have with us Stefan Edelkampf. So first time I met Stefan was in 2012 in Niagara Falls. We replaced my keynote with his keynote. We had to switch because I had problem with planes. And Stefan, since 2012 on our meeting, he started to work on Monte Carlo research applied to a difficult optimization problem. But he has many other activities. So he is well known for planning research, for algorithmic engineering, and for artificial intelligence, and the use also of machine learning with all these problems. So today we have Stefan. So he's professor at Prague University. He was before at King's College, and we welcome him today to tell us about multi-goal motion planning, so motion planning for robots. So, Stefan, the floor is yours.
Okay. Bonjour. Je m'appelle Stefan, but we'll switch to English because it's easier for me. But it's great to talk to PRAIRIE and AI in Paris. So what I want to talk about is multi-goal motion planning, but the news also is that I have just submitted a PDF to Springer, and this is more a bigger scope than my first book on heuristic search, which is like A-star algorithm. It's a wonderful book of 800 pages, but here I switched to a more general, holistic approach on intelligence, and I wanted to emphasize that the algorithm makes a change, or the computers makes a change. It's not always that it comes from heaven or from your soul, that AI dream that everybody is aware of. So we were more on the foundation of computers and integrate programming and so on. So just have a brief view what's coming up. This is having like several parts, this book. One is programming, shortest path sorting. So I have a good sorting algorithm. If you have any things on your desk that need to be sorted, then take my quick merge sort algorithm. It is better in theory and practice, or my the blocked quicksort, which is twice as fast as the ones you have in the STL library. Then the work also with Tristan in deep learning, Monte Carlo tree search, graph data, and so on. I will not talk about everything here. I just took one topic of it. It is more this robot motion planning in application, and we will look into that. This is joint work with several people, but let us just look more closely to where we are. So there's once the planning community in AI, they usually talk about discrete world, discrete action, logics, propositional logic, linear temporal logic sometimes, and AI planning languages. And it's a discrete planning layer, and usually you have long-term planning, but more on the logic level, on the number level. But in motion planning, which is the same word, like planning, but I understand the robotics people understand totally different. So they have a continuous world, they have continuous control and dynamics, simple tasks, usually pick and place, highly dimensional, nonlinear dynamics, physics-based simulation, hybrid solution, and so on. So there is what is needed is somehow to bring the two together, to have a synergistic combination of discrete and continuous layers of planning. So the driving research question in this area is how can we improve motion planning for complex systems? How can we develop motion planners that are generally applicable? How can we achieve planning efficiency even with nonlinear dynamics? How far can we push the curse of dimensionality? How to integrate domain-independent planners for more flexible task planning, how to solve the inspection problems, how to combine efficient discrete solving with searching the continuous space, and so on and so on. And also how to take resource and energy constraints into account. So we will try to follow some approach which I think is pretty good in terms of efficiency, and it really solves some problems in real time that were out of reach for a long time in a scalable fashion. And so let's look around into it and feel what has changed. Okay, this integrates, and also ongoing work is to have it in the sub-T challenge. This is the upper right corner. It's a DARPA challenge from the US, where we have participated as CTU with some robots, also this Boston Dynamic dog, spot robot, they call them. And we are also in changing some machine learning to the basic algorithm RRT star, some emergency planning if like thrust is gone or so, some location routing and so on. So this story will continue. But let us first dive into it. So first we were talking about traveling salesmen and tours. So this is well known to OR community, operation research, and let us just look into it. I think everybody will know the traveling salesman problem. It's a very known problem of my favorite country. It is Germany, and you have some customers around in Kassel, in Cologne, in Frankfurt, in Stuttgart, Munich, and so on. And you have to find the shortest path or shortest tour that connects all of the cities. Previously, you may have condensed the map to having the shortest path between every two of your customers be pre-computed and between your position two. And what you have to have is a minimum cost round trip visiting certain cities. So after the shortest path reduction, you more or less have a matrix of city to city distances of shortest path. And what you have to find is a tour that minimizes the sum of the shortest path. So there are lots of TSP variants which are important in operation research and in practice. So you can have like time windows. We have looked into that, where you have to be within some certain time at your customer. You can have capacity limitations on your vehicle. Could be a lorry, could be a bike, and so on. So you cannot put everything inside. You could have pickup and deliveries. That's to the right upper corner, where you have to pick up some goods from one customer and bring it to the other one. And so you first have to visit, of course, the pickup location before you visit the delivery location. You could have premium services as Amazon Prime to deliver in one day, same day delivery. You could have also multiple vehicles, like an entire fleet, could be homogeneous, could be heterogeneous, and always you want to find good routing among that. This TSP problem is known already for some time, but still there is some improvements in the solving of the discrete problem in this case. So one improvement I came up with was, as you can see, as in the filling, in this case, it is filling like the smiley in with some color, so some color filling. And the idea here is to go like into one direction first and then the other direction. And the reasoning is that in the memory, in the RAM, random access memory, the memory locations are closer together so that the access to these cells are faster. In some cases, it makes a difference between a randomly jumping back and forth in the adjacency, but doing it in this case y-axis wise, and this will improve your algorithm sometimes by factor 40 or so. If you try to use this idea for shortest path, we call it flat filling algorithm, and I really have good implementations for shortest path. So I was working on Fibonacci heaps, pairing heaps, radix heaps, and so on. And the flat filling algorithm actually does better than most of them, at least in this grid type of worlds, as you can see in the figures, that it has some performance improvement. And the other ones are quite advanced algorithms too. So that is one of shortest paths here. That is one that Tristan may like most, that we often play around with NRPA, this nested rollout policy adaptation. It's not an invention of Tristan. It's, I think, by Rosin. It's Ichkai, what, 2011 probably, best paper. And it has solved some previous combinatorial problem for the first time. But many upfollowing and also the precursors are by Tristan. And so it's called nested Monte Carlo tree search with policy adaptation, or only nested tree search with policy adaptation. Actually, it's not a tree search at all. Nested rollout policy adaptation is probably the best wording. Okay, and in this case, you have a recursion tree and you have rollouts that in Monte Carlo is often the case that you roll out, and usually in UCT-like algorithm, you grow the tree differently. Here it is more or less that you have fixed widths and a fixed depth, and you start from like in TSP with an empty tour, and then you roll out fixing the tour. And this idea is quite advanced, and it can get you close to optimal solution in very short amount of time. Of course, you don't have a proof for optimality, as it always is in these randomized algorithms, but the performance is pretty good and can compete with the other large neighborhood search, especially if it's not only the TSP problem, but a higher constraint problem. So if you have any question, you just have to stop me, because otherwise I will talk all day. Okay, here we have some results, initial results, and also some pseudocode where you can see that the nested rollout policy adaptation calls itself somehow here, where you go one level down, and so if level goes to 0, then you do a rollout, evaluate the rollout, and you more or less on each level of the recursion tree, you maintain a policy, and therefore you get a mixture between exploitation and exploration. And here on the graph, you can see with level 1, you probably learn nothing. With level 2, you learn smoothly. And with level 4 or 8, you fluctuate too much. In this case, you will reinitialize the policy too much. But depending on the problem, the level of search is something that you have to look for and optimize. We also had some things in multi-agent systems. There's not much here in the talk, but just to show that if you give this nested rollout policy adaptation algorithm to the lorries in some, or to the buses and taxis and also people in this case, it is, I think, even in Bremen, where my children live. And so you can simulate the entire world. And we also had the shortest path algorithms available for route finding, for multimodal route finding, so that you can simulate the behavior and also some traffic jams and so on. So people will get on trams and buses, and you could simulate if there is some accident or so and how to react to it. So in this, the multi-agents are actually trying to negotiate their tours from one to each other, and this also works in the logistics case. Like for a big company, Hellman, we had such a solution. But let's get back to robots. This starts with Erion Placou to the left, and Erion is quite keen in computational robotics, he calls it. And the main purpose of the physical traveling salesman problem is now that you don't have only the distances, but also acceleration and also heading of the vehicle. So you have a robot, and it has to collect, as here in a game-like scenario. So it was on a game conference. It has to collect all the waypoints that you can see in a smooth manner. So not always the discrete shortest path is best, but because you already have to accelerate, you have to avoid hard turns. So to reach the waypoint location, you have also to avoid obstacles. Planning such as motion requires to take into account the robot geometry, which in this case is quite simple. but as well as the constraints imposed by the dynamics. So this is a very simple game-like scenario. You can view it as a computer game, and you have to steer the Starship-like thing and collect all of the 50 or 30 waypoints here. And this has been extended to have lava and some multi-objective criteria, and also some fuel station when you run out of fuel and so on. So the idea was, or this competition was run at SIG, the Computer and Games Conference, and it has died out after this. But the problem is still exciting, and some of the solution you find in there you can transform. Here you can see that we have added colors to it. So in some cases you want only one of the waypoints in a group to be visited. Or you want first one group to finish before you open the next one, and so on. This could be interesting in inspection problems and so on. And you could have mazes, and here you can see that it's physical because you generate trajectories. You also will slide with the Starship. And here we go into inspection, and inspection of probably by Nord Stream 1 and 2, you know how important it is that your oil pipelines are in order. Inspection is really $1 million industry. So your bridges with drones, or even wind mills with drones, if you want to inspect them, you have to cover like 99 to 100% of the area. And we have started up with doing that. You see a purple area, you see a blue area, and you can see that we generated the waypoints in a way that it sees almost everything. When visiting these waypoints and thinking about having 360 degrees of vision and adding up this, then there's only a few spots that you can see that are not visited. And so finding these waypoints and minimizing these waypoints is one of the objectives in inspection. So here's only one vehicle, but you can think even of several vehicles doing it. So, and the colors impose that you first have to open and visit one color before entering the next color, which is valid for the solution you see to the right. So it can have tremendous economically loss. And the inspection problem is one of the most important problems in robotics nowadays. And here we can see that for the solving process, we actually invited depth first branch and bound with some heuristics. So this is an algorithm more or less branch and bound, but yeah, it's more within the heuristic terminology. You can look at Korf's paper on depth first branch and bound. But it's you have lower bounds, or you have 0 as a lower bound, and you try to find it. And in this case, it happens to be quite good. Random is sometimes bad. Monte Carlo is not the winner, but still giving you good results in this setting. So this was our first initial experiment to find out if we can make something out of it. But next, we went from this image-like scenario, we went to a more complex scenario, a framework, we call it. And this has been developed by Erion for years. He is also the inventor or one of the contributors to move it in the ROS, the robot operation system, but then he continued on his own in this framework, and so it's really scaling well. So this is general robot dynamics, and here the colors have been replaced by numbers, and you see that it's like a remote control car that has to visit all of the groups, and it is limited by the physical constraints. You can see it here that it will go up and down, and sometimes it has to repeat. So there is physical motion involved, and it still can finish this multi-goal motion planning problem and find all of the goals. So that is visibility. So we had different robot models like this car, a snake, or a blimp, even even we also had a quadcopter. And so what we applied is general sampling-based motion planning that comes from more the robotic side, where you have a black box function and you probabilistically sample it to make it feasible. It's a high dimension because the degrees of freedom you are having, but you couple it with discrete abstraction so that you have some guidance on where to go. And you have motion controllers opening the black box function and facilitate search and expansion. Sometimes you get formal guarantees, but I'm not diving into that one. As a basic to start with, you can have like triangulation or any kind of workspace decomposition. What happens to be the most often used in robotics are probabilistic roadmaps. And just to show how a probabilistic roadmap is generated, you just throw some random points to your search space, look which ones are inside your free space and which ones are outside. Then you try to connect them to neighbors. Some are not possible to visit. And then you can connect this to a graph. You have a starting and goal location, and then you have a discrete problem, a discrete routing problem, and then you search for the start to goal. And so that is how you do the path search in a probabilistic roadmap. Here we have it a bit more complicated. We also have obstacles. So we ask for collision every time. And collision is something which we actually get down to the physics engines, so that they can do like the gaming engines as Unity or so. They usually have physics engines, bullet and so on, that they ask for collision. So you can have even complex robots and also differential equations to run for you. So this was for the snake, like each trailer of the snake, it's more like a train. You have like differential equations, and it could also be a robot model that comes from real robotics, but often we deal with this differential equation. So if you look at the dynamics and the complexity of the problem, so what you have to do is you necessarily have to plan motion that can be executed, and that imposes significant challenges to you. So you constrain the feasible motions. So you're often nonlinear. I want to just check if everybody is there. So are you still out there?
Yes, we are still there.
Ah!
Yes. We are listening to
I'm
you.
talking to my computer all the time. Okay, so let's continue then. If you have questions, Tristan, on all the others, please don't hesitate to stop me. Okay, so the robots, they have some different features, non-holomorphic. I often do not understand what it is, but it is important for robotics that we can deal with. I think this is about the controllable parameters that you have. And so these are continuous, solution trajectories are often long, and you have really lots of challenges because also your motion is non-linear. If it's linear, then it would be easier. If it's Newton dynamics, then, well, it's still combinatorial tractable or intractable in some case, so it's NP hard, but it's at least solvable. Dubin's car, which is so half cycling method that my colleague came up with. It's decidable, but he does not handle well the obstacles. And general nonlinear dynamics is undecidable. So how do we solve these challenging problems at all? So the idea is, as my book suggests on heuristic search, is to use a discrete layer and to find solution to a simplified problem and solve it. Here you can see it in terms of colors. That here's a snake and there is a blue area, and where it is red, there is also the goal area. So it starts blue and it has to find a way to the goal. So in this case, it's only one goal. And you can probably discretize it to triangles and solve these triangle distances first. And you do not have like a highly dimensional space, but you can have some some adjacency representation, a decomposition, and you compute distances in the simpler case, and you will use it for the continuous case. Let's get to robotics. Some people of you might not know it. Sampling-based motion planning is similar to this randomized roadmap. But it's a bit different because it generates a tree. So algorithms like RRT star for randomly exploring trees. These were quite well known to robots because they scale also with feasible motion in higher dimensions. So what they do is they sample some point, try to find some nearby feasible motion, and if they get stuck, they backtrack, and with some luck they will reach the goal after some time, and then you have a shortest path also. So you expand a tree of collision-free and dynamically feasible motion. So you select a state, expand the tree, sample the control input, and generate a new trajectory. So it's more a backtrack version of this, but you always have feasible motion. So what is the idea then? We have to find some interplay between the continuous and discrete world. So you need sampling-based motion planning to expand the motion tree and then select some equivalence class to your discretization or where to expand it to somehow guide the search. So here you can see at least the idea in work. So you can see that we are exploring the state, but we are exploring it in the direction of the goal, as A*-like algorithms will do. And after that is found, then we can use actually this representation. So we more or less go back from the continuous layer to the discrete layer on force. So it's back and forth between the two. So you have a tree where at the leaf of the search tree, you solve the discrete problems like thousands of times if it happens. And then you use this as guidance for the overall, like the more complex search. And this turns out, if you do it correctly and with fast solvers on the leaves, that it's quite good. So you would do some equivalence class partitioning, if you like maths, that yeah, so that if you are in the same region, then you have that the trajectories are the same, so that you can map while exploring the search tree things to the region that you are looking at. Well, here you can see more what's coming out in 3D, but you have to look more careful. There is a quadcopter. There is something moving in this slide. It's from two different perspectives, and we have generated these waypoints before using our inspection waypoint generating idea. These are highly scaled industrial objects where we had like 3D meshes from, and so we pre-computed either from the inside or from the outside, pre-computed this, and if you overlay all the inspection areas, then it can see like 99% or more of the entire object. So you can inspect with a quadcopter, it has to be a mini quadcopter, of course, these areas. Okay, here you can also see that in a 2D setting, it is more easy to follow. So here we also have colors, and here you can see that we have to compute vision. So the visibility graph in between, and we generate the point in a way that it almost sees everything, and it has to follow the entire thing by following also the color precedence. So if you start with purple, you have to end up with purple before you start entering like cyan here. And you can see that it almost covers everything. You assume like 360 degrees of vision, which probably is not there, but then you have to adapt these algorithms. And everything is computed within this motion tree so that we can actually generate feasible motions so that the snake does not get stuck. And also you cannot assume 100%, this is a figure to the left, because sometimes the robot physics does not allow to find everything. So you can also spot some parts within the figure that have not been visited or correctly. So there might be something hidden in there. But this is the inspection problem and how it will deal with. So we first generated some skeleton. So this is a 2D idea, a skeleton generation. So this is also called medial axis. These are the distances from the border of your object, and there are some algorithms around, and then you look at the intersection points and try to minimize. So in this case, they probably have not been minimized already, so you may throw away one or two to get a smaller number of waypoints, but still visiting a lot. So the algorithm to find out the skeleton is quite nice, so I decided to put it into the talk. It's called a grass firing algorithm. So at the edges or the border of the object, you put on light or fire, and then it will make its way to the middle, and where the hottest area is, then there will be like the skeleton. As you can see, the skeleton of some different objects and women, so that you can use that for determining possible waypoints. The algorithm, I will not go into it, but just to show that at least for an image, like a 2D image, it's quite fast. It's a linear time. You go forward and backwards one. So it is actually a fast algorithm to generate the skeleton in 2D and on a pixel map. And if you don't have a pixel map, you can get it differently, or you do so. So you get the skeleton, you get your inspection points, you get some visibility score, and then you try to throw out one point after the other and to get a new score and so on. So here we have some more. This one is, we already saw this one. Oh, okay, it does open YouTube. Okay. Okay, there are lots of these things. Let me just look whether we can find more of them. So you can, at Erion's site, you can see lots of the videos, but let me probably stick to the talk that we have here. So where you can also, like in this tower example, not only inspect from the inside, but also from the outside of your algorithm. Here is, I think you can see some outside things and some inside. But you have to have good eyes. I'm not sure if you can see it on your computer. So because there is some some things, but you can imagine that given any 3D model, we can generate those trajectories that really look at it. And you can sample this initial waypoints also without the skeleton. So you can sample some random points close to your objects, or according to your visibility constraints. And the minimization does also not only be the minimization does not only be dropping one off, but you can try to use combinatorics to solve it. Here's a 3D version of the skeleton algorithm. You can find it in CGAL, Computational Algorithmic Library. And then you can also try this one that we have chosen to find our skeleton points, but there are different options. The good thing is that we can use or reuse this Tristan-like single agent rollout policy adaptation algorithm. When you have the S, it's a bipartite graph. On the left hand, you can see like the skeleton points or any points where the robot, where you want to inspect. And on the right hand, this might be like all the vertices of the mesh that you want to see. And there is a bipartite graph. You have an edge from the left side to the right side if a skeleton point sees a mesh point from the inside or outside. And then what you have to do is to compute a hitting set. What is a hitting set? A hitting set is an exact cover, so it should see everything on the right-hand side. So it should be like surjective in mathematical terms. And on the left-hand side, you try to minimize the number of points. So it's a kind of matching problem, but you minimize the number of points that see everything on the right-hand side. And these are usually weighted so that you can find it. And you can use, it's a combinatorial problem. It's known to be hard, like NP hard, not undecidable. And you can use nested rollout policy adaptation with this bipartite graph, and you find like good solution in very short amount of time. And so you minimize your set of waypoints. Okay, I have still some time to get you into temporal task motion planning. So time is money, everybody knows. And here you can see the situation in Amazon warehouses where you have like several robots that bring these shelves to the picking stations. And it's exciting because there's like hundreds of robots in one hall, and this helps then the people at the picking station not to walk all the time, but to concentrate on picking. And there is so many problems involved, like replenishment, route planning, and so on, that Amazon decided, this is, I think they bought Kiva Systems, and it's called Amazon Robotics. They decide to do it on a grid. So what they don't do is, at least as I know, they don't look at acceleration and deceleration. So if two robots meet, they stop and say, oh, okay, probably I will go to the side that you can pass by myself. So it's a grid-like problem. And what we have done is to extend the setting more to a motion or to a general robotic setting. And we also added time windows. So we, instead of only the obstacles and so on, the goal regions, we now have also time window, which is the interval where we want to visit one of the goal areas in our traveling salesman problem or physical traveling salesman problem. So we need a temporal planner that can deal with time. And we can also try to use a general purpose, but we also have a Monte Carlo type planner, and with time windows, the Monte Carlo aspect gets more and more into play. So the traveling salesman problems are getting the solution with Monte Carlo tree search gets better and better. So you will do the equivalence class, a motion tree, and do what I've said before. So you select the equivalence class, and then you go to the simulator and start off again. This is what we also tried, because I'm a professor in AI planning, to deal with general purpose planners. So can we model like the discrete problem also as a general purpose planner, so that we can change more without even looking at the code, like the implementation code? Otherwise, you would have to implement everything anew. And can you formalize it into what we call PDDL, problem domain description language, and extract from this derivative actions, extract somehow ordering, in the sense that we know which customer to search for, which goal areas to search for first with the robot, and then give it to the robot. And this planner is called over and over. Not many planners can do it, but some can. Ours is Optic. It's probably the best temporal planner around. And you can see, you can model it in a list-like scenario. That's what planners in their competition like to do. They have this list-like representation. You do not know what to solve on the planner side, but you can parse these inputs and try to find solutions. So very general. Here we also have like not only time windows, but capacities, pickup and deliveries, all encoded into the problem, and also Monte Carlo solver to compare with. So you can see that nested rollout policy adaptation is doing best. So it solves most of the problems. And so this is, I think, two snake and car in two scenarios, in scene 1, scene 2, scene 3. So A, B, C, D, and you can see branch and bound is not too bad. So it's doing okay. But the general implementation in the planner is also solving some of the problems, not the harder ones where we have like 30 or goals, but it can solve some of the problems. And the optimal one runs out of time, and the random one, it also has problems to solve anything good. So the general purpose planner is not as good as the domain dependent one, but still it gets you some solutions. And this is also true for the second scene. The picture is mostly the same. And in the third, it's also the same. But NRPA as a special proposed implementation is really doing well. What is next is combining task with motion. Here you can see some nice pictures were somehow pancakes. So it's a sliding tile puzzle in some sense, where the robot will collect some of the pancakes and then tries with the obstacles to bring it to the goal location that was written on this pancake or the plate. And when it has done this, then it has solved the entire problem. And so it has to do a pickup and put down a replacement task with motion. And it's very close to a strips-like logistic domain that planners do look at, but now with motions, and you can see it sometimes takes turn. So we have 3/4 of an hour. We still have some slides. You may relax a bit. We are getting to more aspects of this approach. So another wonderful thing is that you may try to apply it to multiple robots. As said, in the Amazon setting, there are like 500 robots around in one factory or in one hall. And is it possible, these algorithms also to scale? In this case, it is not a multi-goal, but a multi-robot exploration problem. And you can see there is like 16, 17, 18, well, starting at 0, it's actually 19, 20 robots we have in form of, what is it, a trolley, and they have to reach their destination. So there are small numbers on them. They have to reach their respective duration. So this is a randomized roadmap generated first, and then you can see that some reach their location pretty early, in which case it gets red. And some to the upper part, you can see there is some problem. The 5 wants to go up and the 19 wants to go down. 19 is there, but it has to bypass the 5. Otherwise, the problem would not be solved. So it now has to rearrange a bit. So it's a multi-agent path-finding problem, but only at the leaf of the trees. Still, there is motion on top of it. So you have a motion tree, and the leaves are called multi-agent path-finding problem. And question is, I haven't seen it so much. Can you extend it also to multi-goal, multi-robot planning with time windows and so on? So we are working towards this direction to include more robots to our research. Here you can see that it's also capacity and item load is something. So if you have goods, I think we also have an animation, lots of videos today. So there's time windows, so it cannot get everywhere at every time, only if the time, like the clock that the car has, fits into the time windows there. And you can see it's a pickup and delivery problem. So if it picks up, it still needs to know that it has to deliver. Okay, we have accelerated, I think, it a bit. So it collects a lot of items. I think the limit of the car is quite high at this point, but could be smaller time window, could be shorter and so on. But you can see that it's a logistic problem. It is solved in operation research for years by now, but in a robotic style fashion where you have also item load and other things. And let us just finish for the sake of seeing it. So it now has to deliver another. So also meeting the timing constraints. Sometimes it has to wait even. Okay, so getting better and better. So finishing soon, only 4 to go. 3, 2, 1, and the last one, which also has the highest timing window. Okay. And there is another one. So, and we also compare Monte Carlo, like NRPA type with the planner. And you can see NRPA or Monte Carlo tree search still is best in scaling. So these are 6 to 30 goals in different scenarios. Mean runtime is in second. So the entire simulation runs for 30 goals in 16 seconds is everything, pre-computing shortest path, doing the traveling salesman, doing this motion tree, doing this abstraction, solving these problems over and over again, simulating this in a simulator and so on. So after 16 seconds, and this is almost real time, it can solve problems of size 30, which is state of the art still, as far as I know. The planner, the general planner, is not as good, but of course you do not have to program anything for that. You only have to model. You can see it can solve up to 1820 within feasible time, and random bails out much quicker, so it can solve 10 and then it is lost. So you can also see when doing some analysis, when you make the time window smaller, then you fail. So it's not only that you can solve this problem, but you also want to optimize, which is in the traveling salesman, it's called price collecting traveling salesman problem. So you may not make it. In the AI terms, it's called oversubscription or preference or soft goals. So that you want to visit all the customers, but you may not make it, then you at least want to finish according to your business goals, finish as good as possible. So there are some things, if the time windows are too short, here by 0.05, then you may miss 2 goals. And the distance is also, of course, maybe larger if you have tighter time windows, because you will have to work harder on meeting the constraints, and the runtime of the algorithm may also depend on that. Okay, so adjusting the time windows gives you a different solution, but also adjusting the vehicle capacity gives you a different solution. So it's almost unlimited. Then you can solve, like if you have 100% of capacity, then you need not much time to compute the entire thing, and you also miss no goals. And the distance may be something, because you can visit most of the goals. And on the other hand, if you have only 40% of the capacity, you have to deliver things earlier to have a free van or lorry. And so adjusting the vehicle capacity gives you a different solution. This is also known as a vehicle routing problem. And here it's only that it is physical, that there are motion constraints and nonlinear robot models. In the PhD of my, of my doctoral student, he also considers energy, and he's defending, I think, in May. So may the force be with you. Yeah, this is the Star Trek day. So here it's the energy, and as you can see, energy is depleted, is getting down, and you have to reach petrol station or battery station, whatever you interpret it, before you run out of energy. In this case, he hasn't visited the second one because he knew that he will reach the goal within the amount of time. So energy is important, and could also be one robot giving the other one energy and so on. And this is in robotics experiments. Even you have the best robots that you see in Boston Dynamics, they usually run out of power in 15 minutes. So we have nice clips, but for long-term, energy is a really important issue. And recharging, so there's multi-goal motion planning with multiple recharging stations. So it's also the location, so where to put the recharging station. So it's also what is called location routing. So you have obstacles. You have the robot that has to visit each goal with reducing the distance and also the number of recharges. And you could add to recharging, you could also do adding temporal constraints. And then you have recharging and time windows. And of course, the combinatorial space for that is big. But still, we are more or less in real time. And this is probably the most important message. Even in robotics, you can use these algorithms, and I find it quite important. The results, it doesn't really matter what the bar says. The only thing is that the purple ones are pretty bad. This is RRT or RRT star, the most favorite one or famous one in robotics. And you can see that it bails out quickly. So the idea of having discrete abstraction and solving it scales your algorithm so that you know where to go with your exploration of these randomized roadmaps. So RRT star is still the one that everybody knows, but to combine discrete and abstraction together with continuous motion, I think has better scalability option and is better. So what we have is a full-fledged solution of high-dimensional robotic system with nonlinear dynamics and non-holomonic constraints, and it visits all goal region in a fast and suitable cost-minimizing order in an unstructured and complex environment, efficiently computes collision-free, dynamically feasible, low-cost trajectories that enable the robot to satisfy the task. So more or less, this is the end of the talk. I will give you like 2 or 3 more slides, and then we are done and get to discuss things. So what we are aiming at now, just to give you an idea, is on vehicle routing with several vehicles. So now you have the operation research vehicle routing problem on robots, and it's also with pickup and delivery. So this is one of our objects at the moment. Then another object of another PhD of mine is deep RRT star. And this is an algorithm that here on the top you can see RRT star. It grows as tree. So sampling-based motion planning. The blue things are the obstacles, and you can see that the tree is quite large. If you use neural network and train it, then you can see in some cases you can minimize the time. Well, of course, the training time is larger, but once you have trained and you can use like transformers and what is it, diffusion models, anything what neural networks come up with, you can use, and you can get like pretty good results learning from a few samples and finding some good solution for your exploration problem. And this is helping us a lot. The big picture we have, and we started up, is to use Unity. So it's a gaming engine that probably everybody knows in the audience. And Unity has started with combining itself together with the robot operating system that every robotics people know about. And so you can adapt robots to Unity and steer them from Unity side, because it has been a client-server architecture and so on. So you can even do real robots, and you can simulate them in Unity. So you can build up scenarios and so on. And that's what we do, and getting better and better in there. Like 2D environments takes a while to implement all this, but to get all the things that you have seen in this more robotic-like scenario. And I think from a practical point of view, this is nice. Here you can see that you also have sensors in, and this would be quite tedious to compute because Unity also have rigid bodies. They have like lots of things, gravity that comes for free, this physics-based engine. And you can see on the right-hand side, you can see how the communication to ROS is, and our exploration algorithms too. I think that's more or less is, because this one is more blue sky to go to more, say, geometric reasoning. So let us stop here and discuss a little bit more on what you think of what you have seen, if this is the right direction in robotics to go, if I really getting to steer the robots in the 21st century, or if it's a dead end. So thank you for your attention.
Thanks a lot, Stefan, for your talk. Very inspiring on a lot of things. So maybe I can first ask, is there people asking questions?
Stefan, thanks a lot for the talk. You covered so many things that it's very hard to go into details.
Yeah, sure.
So probably start with small things.
Yes.
You have the skeleton computation using Grassfire. There's also other methods like Voronoi or Straight Sketch.
Yeah.
So when you select Grassfire, what were your consideration? No.
Well, this is only for grids. So what we did actually is, in one case, we make a photo of the 2D scenario from the above and then made work on the image. So the grass firing algorithm is only really working well, and it computes things in the image setting where you have like pixels in the X and Y coordinate. And then you can apply this algorithm. The other thing in the polygonal world, then it's called medial axis that you have to compute. And this may or may not be more difficult. There are algorithms that can do it in 3D. I think there's even limiting cases where it does not really work with the skeleton. But what we found out after some time is that you probably do not need the skeleton. What you also can do is like just sampling around the objects, and also probably take into account that it has limited visibility. So you sample only points close to the object that you want to inspect. And then you apply this reduction algorithm based on this NP problem. What was it? Hitting set problem, so that you can minimize them. So it is just either you start from the skeleton, which already gives you some good candidates, or you start from random. But the hill climbing with the NRPA is, the algorithm for NRPA is quite good to compute the hitting set with like thousands of points on both sides. And it gets you some good reduction and good visibility solutions already. So if you want to find a needle in the haystack, then it's often the NRPA that gives you some good results. So that we at least figured out, but still the skeleton is some part. And I just have included because I like this grass firing algorithm because it's so simple.
Yeah, yes, once you decide where to go, you need to consider motion for robotics.
Yeah.
In that case, you mentioned a search tree where the leaves were maps, multi-agent pathfinding problem, and you have motion search.
Yes.
Up. But how do you compare this with the a hybrid star, where you use motion sampling and you use a star heuristic to estimate how to go?
Yeah, this is close to A star in the sense, but here we have like a mix between feasible motion, which are in the motion tree. So it's in the tree itself, you have feasible motion from one node to the other. So it can be executed on the robot. And on the leaves, we first run a discrete solver. It does solve the entire problem, but in a simplified manner, only to give us a number back on how easy this problem is to solve. And this guides the search into the direction. So it is in the spirit of A star. It is not exactly A star because A star is in the same. So it's in the discrete world also on top, on the bottom. Here it is a mixture. So once you go to the leaf, you swap from continuous to discrete. And once you have the number back, you go back from discrete to continuous. So it is close, but it's not the same algorithm.
Okay, I was talking about the hybrid star. That was a paper from the DARPA competition
Okay.
before. So, but in this case, even the leaf search map itself is NP hard. It may not give you back a response instantly.
This is a funny thing that the solver, you only have like milliseconds. They are fast enough. If you implement them correctly, they are really, really fast. And of course, you have to be an algorithm designer to get your algorithm, like all this pre-computation in the shortest path maps with Fibonacci heaps, all this advanced thing. And the good thing about the Monte Carlo tree search, you have at least the control to stop. You also get anytime solver, in the sense you probably don't get the best solution, but you get a solution often, or most often a pretty good solution that you can try to steer your robot towards. So it's a good combination of algorithm. You don't need the optimum to steer a robot.
Yeah, do you have a paper or pointer for more details?
Yeah. There was a bunch of papers together with Erion Placou. Like, you can Google us too, and then on DBLP, and then you find all the papers that we have written on this subject. Erion has a few more, like this multi-agent something that was Erion's on ICAPS, and we have some submitted. So if it's on your desk, then you can accept it. So there is still ongoing research, but there is also a lot of published research already.
Yeah, the contents you covered today, how much of these are in your book you talked about?
It's just one chapter, but of course I tell a bit. But the algorithm is nested roller policy adaptation. I think in every second chapter we have it somewhere in solving the combinatorial problem. So it is just one application in there. I have 24 chapters of the work I've done. So it's not the best book of all, but I think the idea in the hype of AI to say, okay, please let us at least not only look at this data-driven neural network, GPT type of change in the world, but also look on the algorithm, on what has changed in there and why does it work, and to look on the discrete side of solving. I think it's okay to have some more idea on the algorithmic foundation of these algorithms, because I think this is actually what has made this hype working, is that we have faster algorithms, and we can now compute what we couldn't compute 10 years ago.
Thanks a lot. Some of the results are eye-opening, so thanks.
Yeah. Thank you so much.
Thank you. Are there other questions? So I have a question about a deep RRT star. Does the neural network is specific to the map, or is it a general neural network?
Well, we started this research, and we like the neural. So it was more imitation learning, what they call it in neural network community, where we somehow have some solutions as expert knowledge that you generate probably running a planner, and then you take this as input to train your neural network. This is often the case. But so it's imitation learning. But after some time, we generalize things. So there is, I think this is also from this large language model, where they have not only transformers, which are general, but also what they call diffusion models and so on. So there is more coming up soon on the type of networks, the ideas behind, and so on. But the general picture is more or less the same. We also do not want to have it only for single start to goal, but also for this round trip thing. And we are working on that at the moment. So it's a running PhD. But we look also at the news in the neural networks, and it's sometimes you find something and it works well, but you also have to understand why. So I think this diffusion things are good. We even work on GPT, where you instruct the robot with natural language, and then it will execute some parts and will more or less filter out your sentences to some lower type of instructions for the robot. And this is also working well within the diffusion setting. So also something coming up there, that you do this with natural language to steer a robot. But still, this is hard work. Everything has to be implemented in the Unity and so on. So robotics is often when you need videos to submit and so on. So it's not that fast of research if you stay in a simulated world.
Okay, thanks. One last question for the eating set with an RPA. Do you use a prior?
A prior? No, I think I just run it. Maybe I did. I don't know exactly because it's time ago. But it's pretty good for these algorithms. So it's like a few lines of code only. I think it's really fast to implement. I think you also did some graph search. Didn't you also, besides of vehicle routing, where you got like better results as me, you also did it for, I think, click and so on. Is that true?
Yeah, but yes,
Yeah.
a prior for vehicle routing is very helpful. So
okay. But for this graph type of search, yeah, well, sometimes you can get something from priors. So they are for hitting set. They are at least in some cases you have this. Have in graph theory, you have some results that you can choose. But in this case, it is the problem is simple enough so that you can get good results in milliseconds. We do not want an optimal solution. This is different to your setting. So if you want to solve vehicle routing problems, for example, you want to be as close to the optimal as possible that you can compare with the state of the art. Here we want very good solution very fast. And this is sufficient for the robotics case.
Okay, great. So are there other questions?
There's one in the chat. Or was it?
Yes, maybe in the chat. I don't think so.
There's something with dynamic obstacles. I think you were.
Okay.
There is something of swarm tree algorithm that Arion worked on, not me, and where the obstacles are moving. I have to admit that in our setting, we pre-compute the shortest path with respect to the obstacle. So in some sense, we compile the obstacles away. So we pre-compute the shortest path, and the distances we work on are these fixed numbers. And so that accelerates at least the traveling salesman problem solver, because it likes to have the thing pre-computed. And with moving obstacles, it's difficult. But of course, there is work in there, and we have approached it, or Arion has approached it once, so that is open to research. So you are not wrong. So we assume to have the map available, so we are also not having the wake-up problem. But in the sub-T environment, where you have point clouds, so we are also working on point clouds input, not only on this, meshes. So there is different versions of the algorithm that we are employing. But the robots are moving, the obstacles often are not. But you can think of a game, of course, that is played, and there is some research, at least in applying for, where we have playing a game, and so you have not only one, but also you're in an adversary setting. You want to compete for resources and so on. There is this never ending. If you have the operation research literature, you just try to think of all this discrete solution with motion, and then you can imagine how big this field might be.
Okay, so thanks a lot again, Stefan, for your talk. So rich talk with a lot of things to dive in, and yeah, we'll have a look at your book.
Yeah, when it comes out.
Yeah.
Let's see. The other one is better, but this one is more general. Okay. And at least the beginning of the programming primer you can even use for classes. And I think it's nice to have a look into, but you do not have to be excited as I am. Okay.
Okay.
Good.
Okay, so have a nice day. Thank you everyone for asking questions, coming and listening to Stefan. And I wish you all a good day too.
Okay.
Thank you. Bye.